Welcome again. Today on CheM in 3, we look at the use of hydrogen-1 NMR spectra to elucidate the structure of organic molecules, looking specifically at 3 sets of data that we can extract from the hydrogen-1 NMR spectrum, specifically the high-resolution NMR spectrum. We look to get data on the number of hydrogen environments, the ratio of hydrogen environments, and the splitting patterns, and we recall that the interpretation of these splitting patterns is associated with the use of Pascal's triangle. This data that we extract from NMR spectra can then be used alongside the molecular formula and other spectral data to elucidate or to figure out the full structure of an organic molecule. Let's move in and take a closer look.
And here in this example from the May 2017 IB exam, you're given this structural formula and given this high-resolution NMR spectrum. You're expected to extract 3 key pieces of information and then use this to go on to elucidate or to figure out its full structural formula. One key skill in carrying this out is to realize that these 3 peaks represent 3 distinct chemical environments for hydrogen. The ratio of the peak is determined not by measuring the line itself, but by measuring the length of the integration trace with your ruler. This would give you a ratio of 2 to 3 to 9, which then would add up to the 14 hydrogens and give you the ratio. The fact that each peak in this high-resolution spectrum has no splitting is a very important piece of information because it tells you that the hydrogens do not influence each other.
So once we get this hydrogen-1 NMR spectral data for this molecule and we have its molecular formula, then we can see what information we can get from this high-resolution spectrum to work along with this formula to figure out or to elucidate the structure of the organic molecule. And here we can see the final answer for one very likely structure of this molecule, at least a structure that is supported by all of the evidence from the high-resolution NMR spectrum. First of all, the number of hydrogen environments. Here I've labeled the hydrogens as A, B, and C to identify the various environments. These 9 hydrogens are all parts of CH3 groups attached to a central carbon, meaning that they would all be in what is termed a chemically equivalent environment. So this accounts for 9 hydrogens and for 4 carbons. Then we have this CH2, which is attached to the C double bond O, and this is a separate chemical environment. These hydrogens being attached to the C double bond O would be in a different environment for the NMR spectrum compared to these 9. So this is another 2 hydrogens. And then over here, on the other side of the C double bond O, we have this CH3, which is again in a different chemical environment from A and C. So we call this one B. And everything adds up to a ratio of 2 to 3 to 9. And this is in keeping with the data provided on the integration trace, which gives that ratio of peaks of 2 to 3 to 9 for the 3 different hydrogen environments. Finally, there are no splitting patterns to interpret in this particular spectrum. Let's look at an example like this one. Here you can see this is one distinct chemical environment, A. Here you have another distinct chemical environment, B. And here, these hydrogens are all in their own distinct chemical environment, all attached to this carbon, C. So for this molecule, ethanoic acid, we can expect 3 distinct peaks in its NMR spectrum. In addition to the 3 distinct peaks, we can expect a ratio when we look at its integration trace of 1 to 2 to 3, indicating that there's 1 hydrogen in one type of environment, 2 in another, and 3 in another. So that accounts for 6 hydrogens. So you know you have 6 hydrogens, 3 distinct environments. And to further help you in figuring out the structure or in the structural elucidation, we can look at the splitting patterns. In this example, we had no splitting patterns because each hydrogen was not under the influence of other hydrogens. Notice that here, these 3 were attached to a carbon that contained no hydrogens immediately attached to it. And these two had two neighboring carbons that were not attached to any hydrogens. So there was no influence in the splitting pattern, and we found that there was none. But here, this peak of 3 is going to be influenced by these two neighboring hydrogens. And following the patterns given in Pascal's triangle, we can say that because there are two hydrogens here, this peak of 3 would be split in the ratio of 1 to 2 to 1. And similarly, this peak of 2 would be split because of its influence from these 3 in a ratio, in keeping with Pascal's triangle, of 1, 3, 3, 1. This peak would not be split because this hydrogen is attached to an oxygen, which is then attached to a carbon, and there's no neighboring hydrogen to cause any splitting patterns in its high resolution NMR spectrum.